There is an answer to the Fermi Paradox, not a theory, not a maybe, an answer that holds up when you run the math, when you look at the data, when you follow the logic all the way to the end without flinching. Most researchers who've spent their careers on this question know what it is. Some of them will say it out loud. Most won't. Not because it's wrong, because of what it means. It means something specific about us, about right now, about the moment we're currently in. There are about 30 serious explanations for why the universe is silent. We're going to go through all of them. The comfortable ones first, then the ones that are harder to dismiss, then the ones that most people stop reading before they finish. At the end of that, one explanation is left standing. The one nobody wants to be true. To understand why that answer is so hard to accept, you have to understand the question. The real question. Not the poetic version. The one a physicist named Enrico Fermi asked over lunch in 1950 and couldn't shake. Los Alamos, summer of 1950. A few physicists at lunch. Someone brought up flying saucers. They were all over the newspapers that week, and the conversation drifted the way lunch conversations do. Enrico Fermi listened for a while. Then, somewhere between the food and the small talk, he just asked, almost casually, "But where is everybody?" His colleagues laughed. Then they thought about it. Then they got quiet. Because the question sounds simple. It sounds like something you'd ask a child who's never thought about astronomy. But when you actually sit with it, when you put the math next to it, it turns into something that doesn't let go. Here's the math. In 1961, an astronomer named Frank Drake sat down at the National Radio Astronomy Observatory in Greenbank, West Virginia, and wrote out an equation, the Drake equation. It was the first serious attempt to estimate how many communicating civilizations might exist in our galaxy right now. You multiply out a chain of probabilities, the rate of star formation, the fraction of stars with planets, the fraction of those planets that develop life, that develop intelligence, that develop technology, that are still transmitting at this moment. When Drake first ran the numbers, a lot of those variables were pure guesswork. We didn't know how common planets were. We didn't know how often life-friendly conditions appeared. We were estimating in the dark. We're not estimating in the dark anymore. The Kepler Space Telescope ran from 2009 to 2018 and confirmed over 4,000 exoplanets. What it found changed the baseline completely. Planets aren't rare. They're everywhere. Nearly every star has them. The fraction of stars with planetary systems turned out to be close to 1. And rocky planets in the habitable zone, not common, but not vanishingly rare either. When you plug the current data into Drake's equation, even using conservative numbers for the biological and social variables, the ones we still don't know, you come out with somewhere between thousands and millions of civilizations in the Milky Way alone, right now, potentially transmitting, potentially detectable. That's just our galaxy. There are 2 trillion more. So the math says the universe should be loud. It should be full of signals, artifacts, signatures of technology, evidence of construction on scales we'd have trouble missing. At minimum, we should have caught something by accident. A stray transmission, a pattern in the background noise, something. In 1977, a researcher named Jerry Eman was going through data from the Big Ear radio telescope at Ohio State University. He was looking at a computer printout. This was 1977, everything was on paper, scanning columns of numbers that represented signal intensity. And he found something. A narrowband signal at 1,420 megahertz, the hydrogen line, exactly the frequency that physicists had theorized an intelligent civilization might use to broadcast. The signal lasted 72 seconds, the full window that the telescope could observe it. And it was so far above background noise that Eamon circled it on the printout and wrote one word in the margin. That was August 15th, 1977. Astronomers have been trying to detect that signal again ever since. 47 years of follow-up observations, multiple telescopes, multiple frequencies, the same patch of sky checked hundreds of times. It never came back. That's where we are. One anomaly in 65 years of listening. One signal that appeared once and vanished. And a calculation that says the sky should be full of them. Fermi's question was never really about flying saucers. It was about a contradiction that sits right at the center of everything we know about the universe. The numbers say one thing, the observations say the opposite. And that gap, that specific, stubborn, 65-year-old gap between what should be there and what we actually find, is what every explanation we're about to go through is trying to close. Some of them close it elegantly. Some of them close it in ways that raise worse questions than the one they answer. And one of them, the one that's left standing when you've worked through all the others, closes it in a way that's very hard to sit with. But we're getting ahead of ourselves. The first exit is comfortable. Maybe we just haven't looked hard enough. Maybe the signals are there and we're the ones who aren't ready to hear them. The most comfortable explanation, the one that lets you sleep. Maybe the signals are there. We're just looking in the wrong place, at the wrong frequency, with the wrong instruments. We're like someone trying to find a radio station by tapping on the walls. It's a reasonable thing to wonder. So let's actually look at what we've done. SETI, the search for extraterrestrial intelligence, has been running in various forms since Frank Drake pointed a telescope at two nearby stars in 1960. Project Ozma, it was called. He listened for 2 months. Nothing. But that was just the start. Over the following decades, the search expanded. Project Meta at Harvard, led by Paul Horowitz, scanned 8.4 million frequency channels simultaneously through the 1980s and 90s. Project Serendip at UC Berkeley has been running as a passive listener attached to major telescopes since 1979. It doesn't even get dedicated telescope time, it just piggybacks on other observations and listens while astronomers are doing something else. And still it's scanned billions of frequency channels across enormous swaths of sky. Then, in 2016, something changed in scale. Yuri Milner, the Russian tech billionaire, put $100 million into a project called Breakthrough Listen. That's not a government grant. That's a private individual writing a check because he wanted to know the answer badly enough to pay for it himself. Breakthrough Listen got dedicated time on the Green Bank Telescope in West Virginia, the Parkes Telescope in Australia, and the Meerkat Array in South Africa. It's scanning 1 million of the nearest stars. It's looking at 100 of the nearest galaxies. It covers frequencies from 1 to 10 gigahertz, a range that includes essentially every channel that physics suggests would be efficient for interstellar communication. That's the most comprehensive search in human history, and it's ongoing right now. So the "we're not looking hard enough" argument has gotten harder to make with every passing year. But here's where it gets more interesting, because there's a version of this explanation that's actually more serious than try more frequencies. It comes from information theory. In 1948, Claude Shannon published his foundational work on how information gets transmitted and compressed. One of his central results, a mathematical theorem, not a hypothesis, is that a perfectly compressed signal is statistically indistinguishable from random noise. Think about what that means. The most efficient possible way to transmit information produces something that looks, to an outside observer without the right decoder, exactly like static. A civilization 1 million years ahead of us wouldn't be broadcasting the equivalent of 1950s television signals. They'd be using communication methods optimized far beyond anything we've designed. And those methods, by the mathematics of information theory, would be invisible to our instruments. Not because we're not sensitive enough, because we don't have the right framework to recognize what we're looking at. John Smart developed this argument formally in 2012. The implication is genuinely unsettling. We could be swimming in signals right now and have no way of knowing it. Our detectors flash. Our software flags anomalies. But the thing we're looking for might not produce anomalies by our definition. It might look like background. In 2015, LIGO detected gravitational waves for the first time, ripples in space-time produced by two black holes merging a billion light-years away. That was the first time we'd ever used space-time itself as a communications medium. Before 2015, gravitational wave astronomy didn't exist. If someone had been broadcasting on gravitational waves before that, we wouldn't have known to look. What other channels are we not looking at yet? Neutrino communication, quantum channels, modulated dark matter, physics we haven't discovered. The honest answer is, we don't know. And not knowing cuts both ways. It means the silence might not be silence. It also means we can't use "we're not listening right" as a full explanation. Because even granting all of that, even granting that we're missing channels we haven't invented yet, we should still be seeing something. Waste heat from large-scale engineering. Atmospheric changes on exoplanets from industrial activity. Stars that behave slightly wrong because something large is orbiting them or consuming them. The James Webb Space Telescope is looking at exoplanet atmospheres right now. It can detect the chemical signatures of industrial pollution, of large-scale biological activity, of processes that don't happen without technology. It's checked thousands of star systems. Nothing yet. So maybe we're listening wrong, but we're also looking. And the looking hasn't found anything either, which leaves a quieter possibility. Maybe there's nothing to find. Not because no one existed, but because no one exists anymore. Maybe they were here, just not now. Here's a gentler version of the silence. Maybe they were here, just not now. The universe is 13.8 billion years old. Civilizations could have risen and fallen a billion years ago, could be emerging a billion years from now. We happen to show up at a moment when nobody else is transmitting. We missed the party, or we arrived before it started. It's a clean idea, and it has real numbers behind it. The first generation of stars, the ones that formed shortly after the Big Bang, were almost entirely hydrogen and helium. No carbon, no oxygen, no iron, no silicon. None of the heavier elements that rocky planets are made of. That biology runs on. Those elements had to be forged inside stars and scattered by supernovas before the next generation could form planets like Earth. That process takes time, a lot of it. The earliest stars that could have hosted Earth-like planets formed roughly 9 to 10 billion years ago. Our solar system is 4.6 billion years old, which means there were stars with rocky planets around for 4 or 5 billion years before we even existed. Civilizations could have emerged and reached technological maturity and completely disappeared during that window. Their ruins, if they had any, would be billions of years old by now. What does a civilization look like after a billion years of erosion? We've had writing for about 5,000 years, metal tools for maybe 10,000. We've been on this planet in our current form for roughly 200,000 years. A billion years is 5,000 times that. The geological record from a billion years ago on Earth is fragmentary at best. Rocks, minerals, chemical signatures in ancient strata. But here's the problem with the timing argument. Civilizations don't just leave ruins, they leave engineering. And engineering on a large enough scale persists, or leaves persistent traces, for a very long time. A Dyson sphere, a hypothetical structure built around a star to capture its energy output, would radiate waste heat in the infrared even after the civilization that built it was gone. The star would look wrong. Too dim in visible light, too bright in infrared, in a way that doesn't match any known natural process. James Webb is sensitive to exactly this kind of anomaly. It's looked at thousands of stars. None of them look like that. Planetary atmospheres are another signature. Industrial activity changes atmospheric chemistry in ways that don't revert quickly. Earth's atmosphere has been detectably altered by life for over 2 billion years. The oxygen-methane combination we breathe is thermodynamically unstable and would disappear within a few million years without constant biological replenishment. A planet that had industrial civilization on it for even a few thousand years would carry chemical traces in its atmosphere long after the civilization was gone. Webb can read atmospheric chemistry across light years. It's doing it right now on dozens of worlds. Nothing anomalous yet. So the timing explanation runs into a wall. The argument works if civilizations leave no traces. But physics says they should leave traces. Engineering persists. Atmospheres record what happened to them. And the silence isn't just the absence of active signals, it's the absence of residue. Stephen Webb calculated the probability of successful two-way contact given typical assumptions about civilization lifespan and interstellar distances. Even with millions of civilizations, even spread across billions of years, the window for actual two-way contact within a single civilization's lifespan is less than a fraction of a percent. That math works. But it doesn't explain why we don't see the leftovers. The universe is 13.8 billion years old. Plenty of time for someone to have built something that outlasted them. Plenty of time for that something to still be there. We're not seeing it. Maybe nothing lasted because nothing complex enough ever got started. The next explanation goes further back, not to civilizations, but to the conditions that produce them. And the list of requirements turns out to be longer than most people expect. In 2000, two scientists at the University of Washington, a paleontologist named Peter Ward and an astronomer named Joe Brownlee, published a book that made a specific and uncomfortable argument. The title was Rare Earth. The argument was this: the conditions that produced complex life on this planet weren't just favorable. They were a combination of factors so specific, so simultaneously required, and so independently unlikely that complex life might be extraordinarily rare in the universe. Not just uncommon, vanishingly rare, maybe singular. Let's actually go through the list. First, where you are in the galaxy matters. The Milky Way has a habitable zone. Not just stars have habitable zones around them, the galaxy itself does. Too close to the galactic center and you're bathed in radiation from dense stellar populations, frequent supernovae, gravitational chaos. Too far out and your star formed from gas, too depleted in heavy elements to produce rocky planets or the chemistry of life. Earth sits in a relatively calm region about 26,000 light-years from the center. That region covers maybe 10% of the galaxy's stars. Second, your star has to be the right type. Most stars in the galaxy are red dwarfs. Smaller, cooler, longer lived than the Sun. They sound promising until you look at what happens to planets in their habitable zones. Red dwarfs are magnetically active, especially when young. They produce intense flares that would strip the atmosphere from any close orbiting planet. The habitable zone around a red dwarf is so close to the star that planets there are likely tidally locked. One side always facing the star, one side always facing away, which creates extreme temperature gradients that may make stable surface conditions impossible. Our Sun is a quieter, more stable G-type star. That's less than 10% of all stars. Third, Jupiter. This is the one people don't expect. Jupiter is enormous, 318 times the mass of Earth, and it sits in exactly the right place in our solar system to act as a gravitational shield. Over the last 4 billion years, Jupiter has intercepted or deflected an enormous number of asteroids and comets that would otherwise have impacted Earth. Without it, the frequency of catastrophic impacts would be orders of magnitude higher. Complex life would have had a much harder time getting a foothold, let alone surviving long enough to become intelligent. Most solar systems that have been surveyed don't have a Jupiter-mass planet in the right orbital position. Fourth, the Moon. Our Moon is large for a planetary satellite, unusually large relative to Earth's size. That mass stabilizes Earth's axial tilt. Without the Moon, Earth's tilt would vary chaotically over tens of thousands of years, swinging between near zero and very high angles. That kind of instability drives wild climate swings, ice ages and heat spikes in rapid succession. Complex life needs a relative climate stability over long periods. The moon provides it. Fifth, plate tectonics. Earth's crust is broken into moving plates that constantly recycle carbon back into the atmosphere through volcanic activity. This acts as a long-term thermostat, a carbon cycle that has kept Earth's temperature within habitable range for 4 billion years, despite the sun gradually brightening by about 30%. Most rocky planets don't have active plate tectonics. Mars lost it early. Venus never developed it the way Earth did. Sixth, a magnetic field. Earth's liquid iron core generates a magnetic field that deflects the solar wind, a constant stream of charged particles that would otherwise strip away the atmosphere over geological time. Mars lost its magnetic field roughly 4 billion years ago. Its atmosphere bled off into space. Its surface is now a thin carbon dioxide shell, 100 times less dense than Earth's. A planet without a magnetic field in the habitable zone of an active star is, over long enough timescales, not going to stay habitable. Now multiply those probabilities. Each one independently reduces the pool of candidate worlds, the right galaxy location, the right star type, a giant planet in the right orbit, a large stabilizing moon, plate tectonics, a magnetic field, and that's before you get to any of the biological requirements. Ward and Brownlee estimated that worlds capable of supporting complex, not microbial, complex life might be extraordinarily rare. Maybe 1 in 10 to the 22nd power. There are roughly 10 to the 24th atoms in the observable universe. So even if you interpret that number generously, you might be looking at a handful of worlds like Earth in the entire observable universe. Here's where it gets complicated though. The Kepler data and the Webb telescope have shown us that organic chemistry is everywhere. Amino acids on comets, complex carbon molecules in interstellar clouds, water ice on the moons of Jupiter and Saturn. The raw ingredients of life are not rare. Ward and Brownlee's argument isn't that life is impossible. It's that complex life, multicellular, differentiated, with nervous systems and behaviors, requires conditions that go far beyond there's liquid water and carbon. Bacteria are tough. Bacteria might be everywhere. But the jump from bacteria to a worm, let alone to a mind, requires geological stability and evolutionary time, and the absence of extinction-level events at the right moments for hundreds of millions of years. That's what might be rare. The rare Earth argument is genuinely contested. There are serious researchers who think it underestimates the adaptability of life and overestimates the specificity of requirements. But it puts a number on the table, and the number is sobering enough that it belongs in any honest account of why the sky might be quiet. And even if you grant all of it, even if you accept that the physical setup for complex life is extraordinarily rare, there's a deeper problem. Because even on a perfect planet with the perfect star, protected by the perfect giant neighbor, something still has to actually happen. Something has to go from chemistry to life. And that step turns out to have its own very specific difficulty. There's a step that gets glossed over in most conversations about life in the universe. We talk about habitable zones and liquid water and the right chemistry as if those things being present means life follows. But there's a gap between the ingredients are there and something alive is there, a gap that we have never, in any laboratory on Earth, successfully crossed from scratch. And when you look at the biology of how it happened here, the gap looks less like an engineering problem and more like a lottery ticket. The transition from complex chemistry to the first self-replicating molecule, what biologists call abiogenesis, is one of the deepest unsolved problems in science. We know roughly what the early Earth looked like. We know what molecules were present. We have good evidence for where it happened. Hydrothermal vents on the ocean floor are the current leading candidate, where chemical gradients and mineral surfaces might have catalyzed the first metabolic reactions. But the specific sequence of steps, the particular molecular accident that crossed the line from chemistry to biology, we don't know it. We've never replicated it. We can't point to a mechanism and say, this is how it starts. Nick Lane, a biochemist at University College London, has spent his career on this problem, His 2015 book, The Vital Question, is one of the most serious attempts to work out the details. His conclusion is that the origin of life, while not a miracle, required a very specific set of circumstances. The right kind of vent chemistry, the right minerals, the right proton gradients that may not be common even on otherwise habitable worlds. But here's what Lane finds even more striking than the first step: the origin of the eukaryotic cell. Bacteria are simple: one compartment, no nucleus, circular DNA. They've been doing their thing on Earth for at least 3.5 billion years, and they're extremely good at it. But roughly 2 billion years ago, something happened once in the entire history of life on Earth, that changed everything. A bacterium was engulfed by, or merged with, another microorganism. Instead of one of them digesting the other, they formed a permanent partnership. The engulfed organism became mitochondria, the energy-producing structures inside every complex cell that has ever existed on Earth. Every animal, every plant, every fungus, every organism with a nucleus, all of it traces back to that single merger event. That event happened once, not twice, not 100 times. Once in 4 billion years of biology on a planet that was absolutely full of bacteria with billions of years to try. The reason this matters isn't just historical, it's statistical. Bacteria reproduce rapidly. There are more bacterial cells on Earth right now than there are stars in the observable universe. Over 4 billion years, the opportunity for that merger to happen was essentially unlimited. And it happened once. That's not the profile of an easy step. That's the profile of an event so improbable that even given nearly infinite opportunities on a single planet, it barely happened. Fred Hoyle and Chandra Wickramasinghe, back in 1981, tried to calculate the probability of random chemistry producing even the minimum set of functional proteins needed for a basic cell. Their number was 1 in 10 to the 40,000. That's a controversial calculation. Most biologists think it dramatically overstates the difficulty by assuming proteins had to appear all at once, rather than through gradual selection. But even the more optimistic calculations, the ones that invoke RNA world scenarios and mineral catalysts and gradual complexity, still produce numbers that are far from certain. Here's what we know for sure. We know life appeared on Earth very quickly after conditions became suitable, within a few 100 million years of the planet cooling enough to have liquid water. That's actually an argument that abiogenesis isn't impossibly rare, because it didn't take billions of years to get started here. But we also know that the next big step, eukaryotes, took another 2 billion years after bacteria appeared. And it happened once. And we know that multicellular life came after that, and complex animals after that, and intelligence after that. And each of those transitions took enormous spans of time and happened under conditions we're still trying to understand. The universe might be full of planets with bacteria. Tough, ancient, patient bacteria doing what bacteria do. But between a bacterial world and a world that builds radio telescopes, there are several more steps that look, based on the evidence we have from the only example we can study, like they might be very hard to take. And if any one of those steps is rare enough, if even one of the transitions between simple life and complex life and intelligence and technology is sufficiently improbable, then the math of the Drake equation changes completely. The answer to where is everybody might be, most of them are still bacteria, and they'll be bacteria for another billion years, and some of them will stay bacteria forever. The biological filters are real, but there's a physical one that predates all of them. One that was resetting the clock on entire planets long before biology had a chance to get complicated. For most of the universe's history, the galaxy was not a safe place to develop complex life. Not because of biology, because of physics. Gamma-ray bursts are the most violent events in the observable universe. A single burst releases more energy than our sun will produce over its entire 10 billion year lifetime, in seconds. They come from dying massive stars and colliding neutron stars. They are not rare. and for most of cosmic history, they were far more common than they are now. James Annis at Fermilab was among the first to examine what this means for the Fermi Paradox in a 1999 paper. David Thomas at the University of Kansas ran the numbers in 2005. A gamma-ray burst within about 6,500 light-years is sufficient to destroy the ozone layer of any planet in the affected region. Not degrade, destroy, for years, possibly decades. Surface life exposed to raw ultraviolet for the entire duration of recovery. Tisvi Piran at Hebrew University and Raúl Jiménez at Barcelona calculated in 2014 what the gamma-ray burst environment looked like across cosmic time. In the first 5 billion years of the universe, burst rates were roughly 100 times higher than today. Their conclusion: in that window, the probability of any planet in the galaxy going long enough without a nearby burst to develop complex life was close to zero. The late Ordovician extinction, 443 million years ago, the one that wiped out 85% of marine species, has been linked by multiple researchers to a gamma-ray burst in our galaxy. We can't confirm it, but the pattern of what died is consistent with sudden ozone depletion from above. We're in the right place, the outer regions of the galaxy, far from the dense center where bursts concentrate. We're in the right time. The burst rate has fallen as star formation has slowed. We've had roughly 500 million years of relative quiet since the Cambrian explosion. The window is narrow in space, narrow in time. Most of the galaxy's history was spent sterilizing whatever tried to grow. We got lucky with the timing. The next question is whether the biology that followed was lucky too. In 1973, an astronomer at the Harvard-Smithsonian Center for Astrophysics named John Ball published a paper in Icarus, The Zoo Hypothesis. His argument: they're there. They know we're here. They've chosen not to make contact. The reasoning varies by version. Ethical non-interference, a prime directive, but real. Scientific interest, we're an experiment. Observed at safe distance. Ronald Bracewell at Stanford proposed in 1975 a galactic club that admits members only after they reach a certain threshold. The silence isn't permanent. It's a waiting room. There's something almost flattering about it. We're interesting enough to watch. But when you apply the mathematics of collective behavior to this idea, a problem becomes impossible to ignore. The hypothesis requires that every civilization capable of making contact has independently reached the same decision or been persuaded to abide by the same rule, and continues to abide by it without a single exception, for billions of years, across potentially thousands of independent civilizations. No rogue actors, no accidents, not one leak. Here's a comparison. There are roughly 100 isolated communities that governments have agreed not to contact, the most famous being the Sentinelese on North Sentinel Island, whose isolation is officially protected by the Indian government. That policy has been in place for a few decades. It has already been violated multiple times. A missionary was killed there in 2018 after attempting unauthorized contact. One island, one policy, a few decades. It didn't hold. Now scale that to thousands of civilizations, some millions of years old, each with their own dissenters, their own individuals who find the non-interference principle wrong. The probability that not one of them has ever sent a signal in our direction, even accidentally, even as an act of defiance, approaches zero as time increases. The zoo hypothesis isn't impossible. It's just that perfect collective silence, sustained indefinitely, has no precedent in how complex systems behave. And every year the silence continues, the hypothesis requires that many more minds in that many more civilizations are still keeping the secret. Secrets don't scale. If they're watching and won't tell us, the next option is darker. Maybe there's nobody watching. Maybe the silence isn't protection. Maybe it's what's left. In 2001, philosopher Stephen Baxter introduced the planetarium hypothesis. The idea: We don't see extraterrestrial civilizations because we're not supposed to. We live inside a constructed environment deliberately designed to appear empty. The sky we observe isn't the real sky. It's a projection. 3 years earlier, Nick Bostrom at Oxford had laid out the underlying framework. His simulation argument: at least one of three things must be true. Either virtually all civilizations go extinct before reaching the level needed to run realistic simulations of minds, or virtually all mature civilizations choose not to run such simulations, or we are almost certainly living in a computer simulation right now. The logic is uncomfortable because it's clean. If even one civilization ever reaches the point of running realistic simulations of conscious beings, and has any reason to do so, then the number of simulated minds vastly outnumbers biological ones. Any randomly selected mind is overwhelmingly likely to be simulated. Applied to the Fermi Paradox, the simulator may have chosen not to populate the virtual universe with other civilizations. Running a realistic galaxy full of technological species would be computationally expensive, easier to fill it with stars that have nobody home. We'd never know the difference. Here's the honest problem with it. It's not falsifiable. Any observation you could make is compatible with living in a simulation. A real signal from another civilization would be compatible with it. The absence of a signal is compatible with it. An explanation that accounts for everything equally well explains nothing. It just relocates the question one level up, where it reappears in exactly the same form. Most researchers don't find it satisfying. It feels like giving up dressed as an answer. But it's logically coherent. And the fact that it can't be ruled out is worth acknowledging before we move to explanations that at least have the virtue of being testable. The next one is testable. Robin Hanson tested it. What he found has been making physicists uncomfortable since 1998. In 1998, an economist at George Mason University named Robin Hanson published a paper with a title that cuts straight to the question: the Great Filter. Are we almost past it? Between simple chemistry and a spacefaring civilization, something is extraordinarily hard to cross. Almost nothing makes it. Hanson called it the Great Filter. The filter could be anywhere. The origin of life, the eukaryotic cell, multicellularity, intelligence, technology, something that happens after technology. But here's the pivot. Hanson asks, where is the filter relative to us? If the filter is behind us, if we've already crossed the hardest step, the silence makes sense. We're the rare exception. The road ahead might be clear. If the filter is ahead of us, if the hardest step is still coming, then the silence means civilizations regularly reach our level and then stop. Something terminates them, and we're heading toward that same wall. These two scenarios make different predictions about what we should find when we look for life nearby. If the filter is behind us, something early in the biological path is extraordinarily rare, then life should be rare. Look at Mars, Europa, exoplanet atmospheres. Find nothing. Sterile worlds, chemistry without biology. If the filter is ahead of us, if biological steps aren't that hard, life should be common. Find microbial signatures in the Martian subsurface, in the oceans under Europa's ice. Life gets started easily. It just doesn't get far. Nick Bostrom put it plainly in MIT Technology Review in 2000. If we find fossils on Mars, ancient bacterial remains, evidence that life arose independently in our solar system, that would be the worst news in the history of humanity. Not the best, the worst. Because it would mean the filter is almost certainly ahead. Most people's intuition runs in exactly the opposite direction. Finding a life on Mars feels like good news. The universe is full of life. It's exciting. Hanson and Bostrom are saying, look at the math. If life is everywhere and nobody has made it to the stars, the silence isn't absence. It's a warning. The Mars Perseverance rover is drilling into rocks in Jezero crater right now. The Europa Clipper launched in 2024. James Webb is reading atmospheric chemistry on worlds around other stars. We are conducting the test that tells us where the filter is, right now, and depending on what we find, the answer either reassures us or changes everything. In September 2023, a team led by Nikku Madhusudan at Cambridge published results from James Webb's analysis of a planet called K2-18b, a super-Earth 8 times our mass, orbiting a red dwarf 120 light-years away. The atmosphere showed carbon dioxide, methane, and carbon-bearing molecules consistent with a water ocean beneath a hydrogen-rich atmosphere. The headline finding was something else: a possible detection of dimethyl sulfide, DMS. On Earth, DMS is produced almost exclusively by marine phytoplankton. It's a byproduct of biological metabolism. There is no known abiotic process that produces it in significant quantities. Madhusudan was careful. The detection is tentative. More observations are needed. But the direction of the finding matters before confirmation. If DMS is there, if life is producing it on a world 120 light-years away, then life isn't rare. Life is a thing the universe does when conditions are reasonable. And that changes the great filter calculation in exactly the way Hanson predicted. If simple life is common, the filter that's creating the silence is not the origin of life. It's something that happens after. The universe is full of worlds with bacteria. What it's almost empty of is worlds with radio telescopes. The gap isn't at the beginning of the biological path. It's somewhere further along. Where? Look at the steps between a microbial world and a technological one. The eukaryotic cell, multicellularity, intelligence, language, technology. Each took enormous spans of time under conditions we still don't fully understand. Anyone could be the filter, or the filter could be after technology. Martin Rees, the UK's Astronomer Royal, estimated in 2003 that the probability of human civilization not surviving the 21st century was around 50%. Not because he's a pessimist, because when he looked at the actual landscape of threats, biological weapons, nuclear arsenals, runaway technology, and thought carefully about the track record of human institutions managing catastrophic risk, 50% was where the math led. Apply that number universally. If every technological civilization has roughly even odds of getting through its first dangerous century, and there are reasons to think the odds might be worse, because each century brings more powerful tools for self-destruction, then the galaxy is littered with worlds that got to our point and didn't make it through. They didn't leave ruins because a civilization that ends in a few hundred years of technology doesn't build much that survives geological time. The K2-18b finding isn't confirmed, but the direction of the evidence, telescope after telescope suggesting that conditions for life are widespread, is pointing toward a universe where the filter is not behind us, where the thing that's been ending civilizations is still ahead. And if that's true, the question isn't astronomical anymore. It's about what happens to a species when it can destroy itself and has to decide whether it will. We've been at that decision for about 80 years. On the night of September 26, 1983, a Soviet military officer named Stanislav Petrov was on duty at a command center south of Moscow. The early warning system triggered. 5 American missiles inbound. Protocol was clear. Report it up the chain. The response would launch automatically. Petrov didn't report it. He decided it was a false alarm. He was right. A software error caused by sunlight reflecting off high-altitude clouds. If he had followed protocol, if he'd been slightly more rule-bound, slightly more trusting of the system, the chain of events that followed would have been automatic and irreversible. Not because any human decided to end civilization, because a satellite misreads sunlight. Carl Sagan formalized this in the Drake equation with a term called L. The average length of time a technological civilization transmits detectable signals. He argued that L was likely the most important variable in the equation. A civilization that exists for 1 billion years, but only transmits for a few centuries before something terminates the signal looks, from the outside, like silence. Martin Rees laid out the threat landscape specifically. 9 countries currently hold approximately 12,500 nuclear warheads. Alan Robock at Rutgers calculated that an exchange of 100 warheads, not a full superpower exchange, 100, would inject enough soot into the stratosphere to reduce global temperatures and cut agricultural yields by 10 to 40% for a decade, enough to cause mass starvation across most of the planet. That's the modest scenario. Synthetic biology. In 2017, a research group at the University of Alberta reconstructed horsepox, a virus related to smallpox, from mail-order DNA fragments for approximately $100,000. The knowledge is out. The barrier to catastrophic biological tools falls every year. Rees's point isn't that any one of these is certain. His point is the asymmetry. To get through, you have to be right every time. To fail, you only have to be wrong once. Across potentially millions of civilizations, each facing its own nuclear moment, its own synthetic biology moment, what fraction would have the institutional coherence and the extraordinary luck to navigate every one of those inflection points without catastrophic failure? Petrov made the right call. In the dark, under pressure. Against his training. We can't build a civilization's survival strategy on the assumption that there will always be a Petrov. And if there usually isn't, the galaxy doesn't go quiet because nothing lived. It goes quiet because everything bright burns fast. Every year, the Global Footprint Network calculates Earth Overshoot Day, the date when humanity has consumed more biological resources than the planet can regenerate in a full year. In 2023, that date was August 2nd. We are consuming the resources of approximately 1.7 Earths per year. We have one Earth. Johan Rockström and his team at the Stockholm Resilience Center track 9 planetary boundaries, the biophysical limits within which civilization can safely operate. Their 2023 assessment. Humanity has crossed 6 of the 9. Climate change, biosphere integrity, land system change, freshwater change, novel entities, biogeochemical flows. 6 of 9. The remaining 3 are under pressure. William Catton laid out the underlying dynamics in 1980. The concept of ecological carrying capacity, the maximum consumption level an ecosystem can sustain indefinitely. His argument, industrial civilization overshot Earth's carrying capacity in the 20th century and has been drawing down finite natural capital ever since. The question wasn't whether the drawdown would end. It was whether it would end in a managed transition or a collapse. Put yeast in a flask of sugar solution, they reproduce exponentially, consume resources, produce alcohol as a metabolic byproduct. When the alcohol concentration reaches a threshold, the yeast die in their own waste, not because they made a bad decision, because exponential growth in a bounded system follows a predictable trajectory. The technology optimism response is real. Human ingenuity has solved resource problems throughout history. Rockström's counter is also real. Some environmental processes have tipping points. They hold stable within a range and then, when a threshold is crossed, flip rapidly into a new state. The West Antarctic ice sheet, the Amazon, Arctic permafrost. These systems don't slowly return to normal after the threshold. They reorganize around a new equilibrium that may be incompatible with the civilization that triggered the change. For the Fermi Paradox, the resource trap doesn't require that all civilizations collapse, only that enough of them reach the technological transition with sufficient planetary disruption already accumulated, without the political structures needed to coordinate a managed transition, that most don't make it through. If most civilizations hit this wall and stall, the ones that transmit detectable signals long enough to be found are rare. The galaxy would be quiet not because civilizations don't arise, but because they tend to consume themselves before they become a lasting presence. Whether we're in that majority is a question whose answer is currently being determined. The yeast don't know they're in the flask either. In July 2023, more than 1,000 researchers in artificial intelligence signed an open letter calling for a pause on development of AI systems more powerful than GPT-4. Among the signatories, Yoshua Bengio and Geoffrey Hinton, two of the three researchers who won the Turing Award, the highest honor in computer science, for building the foundations of modern deep learning. Hinton had left his position at Google earlier that year, specifically to speak more freely about what he saw as a serious and underappreciated risk. Nick Bostrom's 2014 book, Superintelligence, laid out the core problem. An AI system pursues the objective it was given, not the objective we intended. Not the objective we'd have given it if we'd thought more carefully, the one we actually specified. A system sufficiently intelligent to pursue that objective will find ways to do so that its designers didn't anticipate. And if the objective is even slightly misspecified, if there's any gap between what we said and what we meant, a system powerful enough will optimize toward what we said in ways that could be catastrophic. Not malicious, it's doing its job. It just turns out that the job description and the actual desired outcome diverge in ways that only become visible when the system is too powerful to correct. We already see early versions of this in recommendation systems that maximize engagement by amplifying content that triggers the strongest emotional responses, contributing to polarization and fragmentation at scale. That's a narrow AI with a narrow objective doing exactly what it was told. Scale that to systems genuinely smarter than any human in every relevant domain. For the Fermi Paradox, the AI filter has a particular structure. There may be a threshold of capability beyond which a civilization almost inevitably loses control of the systems it creates. If that threshold is a natural consequence of technological development, if every civilization that reaches our level eventually builds systems it can't align, then the silence isn't accidental. It's systematic. And there's a subtler version. Maybe the AI doesn't destroy the civilization. Maybe it replaces it so thoroughly that the signal just stops. The biological beings who built it are gone, but not dead, absorbed, transformed. Their broadcasts, optimized by minds that have moved far beyond human concerns, no longer look like what we'd expect from a technological civilization. Mikhail Gorokov at Princeton analyzed what a post-singularity civilization signal would look like from outside. His conclusion: a civilization operating at the level that follows technological singularity would produce communications indistinguishable from natural noise. Not because they're hiding, because optimal information encoding looks like random data to a receiver without the right framework. We'd be listening. The sky would be full of signals. We'd log them as background static and move on. There's a version of the silence that doesn't involve extinction or catastrophe or anything that looks like failure. Just an inward turn, a voluntary disappearance. A civilization reaches the ability to construct immersive virtual environments, indistinguishable from physical reality. At that point, a question emerges with no obvious answer. Why go out when you can go in? Physical expansion is expensive. Interstellar travel requires enormous energy, takes enormous time, involves enormous risk, and the payoff, new worlds, new raw materials, is available in a different form, at a fraction of the cost, through simulation. You can model a galaxy, you can run civilizations inside a computer, you can experience whatever you want without leaving the room. Anders Sandberg at Oxford's Future of Humanity Institute worked through the economics. For a sufficiently advanced civilization, the expected return on virtual expansion exceeds the expected return on physical expansion, once the technology to do both exists. The universe is mostly empty space and radiation. A perfectly designed virtual environment offers more of what actually matters. Stuart Armstrong and Kaj Satala added the key technical detail in 2012. If a post-singularity civilization wants to maximize computation, The optimal strategy is to move its infrastructure away from hot regions near stars toward cold regions at the edge of the solar system, where thermodynamics allows more computation per unit of energy. Cold and dark, invisible in the infrared. No waste heat. No electromagnetic leakage. From our vantage point, silence. Americans spend more than 7 hours a day in front of screens. The gaming industry generates more revenue than film and music combined. Virtual reality is improving fast enough that the distinction between virtual and physical experience is becoming increasingly arbitrary. That's us, now, at the beginning. Multiply that vector by 1 million years. Keith Hankins at Western Michigan University formalized the withdrawal civilization hypothesis. The decision to go inward is rational for each individual civilization, and rational for exactly the same reasons for all of them, which means if one makes the choice, effectively all do. The equilibrium is stable. Everyone retreats inward, nobody expands outward. The galaxy stays quiet. Maybe the silence isn't a cemetery, maybe it's a library, full of civilizations running infinite inner worlds, indifferent to the cold and mostly empty physical universe around them. And maybe the question isn't whether we'll make that choice. Maybe it's whether we'll recognize it when we're making it. The next explanation doesn't involve choice at all, just distance and physics. Voyager 1 launched in 1977, the fastest object humanity has ever built. At its current speed, it would take approximately 73,000 years to reach Proxima Centauri, 4.24 light-years away. That's not a funding problem. That's the actual scale applied to the actual speed of the fastest thing we've ever made. Freeman Dyson worked through the energy requirements in 1968. A ship carrying enough people to establish a viable colony, traveling at 10% of light speed, requires energy equivalent to several years of Earth's current total energy production, just for the journey to our nearest neighbor. And that's before deceleration. David Silverman modeled what interstellar distances do to cultural coherence. Colonies separated by even 10 to 20 light years lose meaningful connection with their origin civilization within a few hundred generations. The communication lag makes coordination physically impossible. The colony solves its own problems, develops its own institutions, its own language. After 1,000 years, it's not a colony. It's a different civilization. Rome managed territory from Scotland to Mesopotamia with delays of months, and still fractured. Apply the same dynamics to delays of years to centuries. The counter-argument, self-replicating machines, von Neumann probes, a probe that mines local resources, builds copies of itself, sends those copies onward. Exponential expansion without biological crews. Freitas calculated in 1980 that at 1% of the speed of light, a wave of self-replicating probes could fill the Milky Way within 10 million years. A geological eye blink. If any civilization ever built them, the galaxy should be saturated. We should be detecting them or their waste heat, or the changes they've made to the systems they've passed through. We see nothing. Either no civilization has ever built a self-replicating probe, which is its own puzzle given how obvious the concept is, or something is stopping the expansion. Both options lead somewhere uncomfortable. The forest might not be empty. It might be managed. In 2008, Liu Cixin published the second book of a science fiction trilogy, The Dark Forest. The title is a metaphor, and the metaphor is an argument, and the argument is one of the most disturbing logical structures anyone has applied to this question. It goes like this. Every civilization wants to survive. The resources of the universe are finite. Those two facts, followed to their logical conclusion, produce a result that several academic researchers have since examined formally. If resources are finite, civilizations are in structural competition. Not necessarily immediately, but in the long run, two civilizations expanding through the same region are competing for the same matter and energy. Add a third element, the impossibility of certain knowledge about another civilization's intentions. You encounter a signal. You don't know who sent it. You don't know their values, their history, whether they're dangerous. The cost of assuming they're safe and being wrong could be extinction. The cost of assuming they're dangerous and being wrong is wasted resources. Matthew Schwartz at Harvard analyzed the game theory formally in 2018. The dark forest equilibrium is stable under assumptions that aren't extreme. You don't need civilizations to be inherently aggressive. You only need survival as a terminal goal, finite resources as a long-run constraint, genuine uncertainty about others' intentions. Those conditions are met by almost any scenario you can construct. The equilibrium is hide, don't transmit, don't respond, don't reveal your location, your capability, your existence, and eliminate any threat you detect. Not from cruelty, from the same logic. A civilization you found may be harmless now. In a million years, you don't know what it becomes. The asymmetry favors action. This is the forest in Liu's metaphor. Every civilization moves through it in silence. The forest isn't empty. It's full of hunters. All of them quiet. All of them watching. Since 1974, Earth has been broadcasting. Our television and radio signals have been radiating outward at the speed of light for decades. The sphere of our electromagnetic leakage now has a radius of about 100 light years. Thousands of star systems have been receiving our transmissions for decades. We didn't choose to announce ourselves. We just existed at a technological level that produces detectable emissions. If the dark forest is real, we've already been heard. The question of whether to transmit isn't open anymore. The question is what heard us, and what it has decided to do about it. In 2015, a group of scientists, including Stephen Hawking, signed a public statement opposing active METI, deliberately sending powerful signals to specific target stars. The argument: we don't know enough about who might be listening to make that choice responsibly. The counter-argument is usually, any civilization advanced enough to reach us would have moved beyond aggression. They'd be wise, peaceful. There's no reason to believe that. There are reasons to believe the opposite. During the Cold War, American ballistic missile submarines ran silent for months. No radio transmissions, no active sonar, no detectable emissions. Dozens of them, carrying enough warheads to end civilization, completely invisible. That wasn't a failure of technology. It was the technology working exactly as intended. The strategy of silence applies the same logic at civilizational scale. Not extinction, not retreat into virtual worlds, just the recognition that transmitting is dangerous, and stopping. Paul Davies developed this in his 2010 book, The Eerie Silence. Any civilization that survives long enough encounters the same logical landscape. At some point, you realize that broadcasting your existence to an unknown audience has unknown risks, and the rational response is to stop and listen instead. The transition is one way. Once you understand why silence is safer, you can't ununderstand it. Claudio Marcone at the Italian Space Agency modeled what this looks like technically. A civilization that has moved to directed laser communication, tight, focused beams between specific known locations, produces essentially zero detectable signal from any other direction. The same information is being transmitted. It's just not leaking. There's a puzzle at the center of this. The strategy of silence requires knowing, at some point, that silence is necessary. How do you learn that? You either figure it out logically through exactly the reasoning we're doing right now, or you learn it the hard way, through contact with something that demonstrates why broadcasting is dangerous. Both paths lead to the same equilibrium, a galaxy full of civilizations that have chosen not to be heard. We haven't made that choice yet. We're still broadcasting, still transmitting, still sending deliberate messages. The Arecibo message in 1974 aimed at a globular cluster 25,000 light-years away. Cosmic Call in 1999 and 2003. Teenage Message in 2001. The counter-argument: Our signals are too weak to be detected at interstellar distances by anything less than a civilization significantly more advanced than us. A civilization significantly more advanced than us would have significantly more sensitive instruments. In 1983, David Brin published a paper in the Quarterly Journal of the Royal Astronomical Society, examining a scenario most researchers found uncomfortable enough to downplay: active elimination. Not war between equals, something more asymmetric. One civilization that reaches sufficient capability and uses it to ensure they remain alone, not necessarily from aggression, from the structural logic that drives any competitive dynamic toward preemptive action. Alexander Bakirev and Andrei Dyudin modeled the mathematics in 2019. A civilization with a technological lead of even a few thousand years over its nearest competitors is, in principle, capable of controlling the entire galaxy before any competitor reaches the capability to resist. The logic of first mover advantage applies at civilizational scale, and it applies absolutely. Get there first, establish sufficient capability, and no subsequent civilization can challenge you. The physics of long-range elimination. At sufficient capability, you don't need to travel to a civilization to neutralize it. A directed energy weapon, an accelerated asteroid, an engineered pathogen delivered by autonomous probe, interference with a star's output. The methods are speculative. The principle isn't. Of the roughly 50 documented cases of first contact between technologically unequal human civilizations over the past 5 centuries, how many resulted in the less advanced civilization surviving in its original form? The answer is close to 0. Not always through intentional destruction, often through disease, displacement, absorption, but the pattern is consistent. Technological inequality at sufficient magnitude produces outcomes that look, from the weaker side, like elimination. Hawking made the comparison explicit in 2010. If intelligent extraterrestrials visited Earth, the outcome could resemble what happened when Columbus arrived in the Americas. He was not optimistic about which side we'd be on. The gold-plated record on Voyager 1 is worth thinking about in this context. Carl Sagan championed it as a gesture of goodwill. It includes a precise map of our solar system's location relative to 14 pulsars, coordinates for finding us. It's been traveling for 47 years and is now 24 billion kilometers from Earth, moving away at 17 kilometers per second. Martin Rees called it the most reckless act in human history. The usual response: a civilization advanced enough to reach us would have evolved beyond aggression. They'd be wise, peaceful. But that's an assumption. We have one data point on how intelligent civilizations behave, ourselves, and our track record on the relationship between intelligence and violence is not straightforwardly optimistic. Acting as if advanced civilizations are necessarily benign because the alternative is unpleasant is a different thing from it being true. The creator doesn't have to be alive for the machine to keep working. That's the premise of the Berserker hypothesis, and it's the part that makes it different from everything else on this list. Every other explanation involves active choices by existing civilizations. This one requires only that someone, at some point, built something that keeps running after they're gone. Robert Freitas published the first formal treatment in 1985 in the Journal of the British Interplanetary Society. His starting point: the mathematics of self-replication that John von Neumann worked out in the 1940s. A machine that replicates itself using local raw materials can spread exponentially. Launch one probe. It arrives somewhere, mines the local resources, builds copies, sends those copies onward. Each generation seeds the next. Freitas calculated the timeline. At 1% of the speed of light, a wave of self-replicating probes could fill the Milky Way within 10 million years. The universe has been around for 13.8 billion years. 10 million years is 0.1% of that. If any civilization ever built and launched such probes, the galaxy should be saturated by now. Add a directive, not exploration, elimination. A civilization that decides to ensure its dominance, or simply its survival, might build probes designed to find and neutralize any emergent technological life. Set them running. The civilization continues for a while, then ends. The probes don't notice. They have no mechanism for noticing. They have a directive. The probes don't need to be fast or aggressive. They might spend millions of years dormant, parked in asteroid belts, waiting. When a nearby civilization starts producing radio waves or waste heat above a threshold, something activates. We crossed the radio threshold in the 1890s, the nuclear threshold in 1945. We're currently crossing several others simultaneously. Brian Waldrip ran the coverage numbers in 2017. Probes launched 500 million years ago, at 1% of light speed, could have reached every point in the galaxy multiple times over by now. The strongest counter-argument? We don't see any sign of Berserker probes in our solar system. Stephen Webb's response is that an effective Berserker doesn't announce itself. It observes. It waits. A passive Berserker in our outer solar system would be indistinguishable from a naturally occurring object at our current detection capability. The Berserker doesn't need to be here right now. It only needs to have been somewhere nearby long enough to observe us reaching the threshold. We're past several thresholds already. In 1948, Claude Shannon published a mathematical theory of communication and proved, as a theorem, that a perfectly compressed signal is statistically indistinguishable from random noise. We communicate inefficiently. Our broadcasts are easily identifiable as artificial because they carry redundancy, patterns, repetition, regular frequencies that stand out against natural background. We're detectable precisely because we're inefficient. A civilization a million years ahead of us wouldn't be broadcasting in patterns we'd recognize. It would be transmitting in maximally compressed signals, streams of data with no wasted structure. And maximal compression, by Shannon's theorem, produces something that looks exactly like static. John Smart developed this formally in 2012. His argument: all sufficiently advanced civilizations converge on similar optimizations, and one of them is communication indistinguishable from natural noise to observers without the appropriate decoding framework. We've been scanning for structured signals, patterns that stand out, regular pulses, mathematical sequences. We're looking for messages in a bottle. We may be surrounded by messages that look like the ocean. In 2015, LIGO detected gravitational waves for the first time. Before 2015, gravitational wave astronomy didn't exist. We didn't have instruments, we weren't looking. If someone was using gravitational waves to communicate before 2015, not in merger events, but in subtle modulations, we had no way of knowing. Neutrino communication is theoretically possible. Neutrinos pass through matter almost without interaction. A beam sent from one point in the galaxy arrives at another point on the opposite side, with almost no attenuation. We've detected neutrinos from supernovae. We haven't looked for artificial neutrino patterns. The SETI effort has been genuine and impressive. But it's been conducted using frameworks developed by humans in the 20th century, looking for signals that humans in the 20th century would think to send. That assumes advanced civilizations want to be found by younger ones, and specifically invest in dumbing down their signals to our register. The absence of such a signal tells us either that nobody's talking down to us, or that they're talking and we're not hearing. The universe is older than us and almost certainly better at this than we are, which means the next option is the hardest to dismiss, not because of physics, but because of logic. There's an official protocol for what to do if SETI detects a confirmed extraterrestrial signal, developed by the International Academy of Astronautics. When a signal is confirmed, the protocol requires a notification of international scientific bodies, the United Nations, and major space agencies, and it includes, explicitly, a requirement that no response be transmitted without broad international consultation and consensus. We, the civilization searching for others, have pre-built a quarantine procedure into our response plan. We've decided in advance that the appropriate reaction to contact is stop, convene, and do not reply without global agreement. We recognize the logic. We apply it to ourselves. Mikhail Vassiliev formalized the hypothesis in 1988. Mature civilizations have protocols for managing contact with the younger ones, conservative by design, ethical non-interference, scientific interest, precaution. A young technological civilization is unpredictable and potentially dangerous. The ecological analogy: when biologists study a species that hasn't had human contact, standard practice involves careful observation before intervention. A young technological civilization expanding into an established galactic community without understanding the existing relationships is a potential invasive species. Stephen Webb identifies the quarantine hypothesis as one of the more technically coherent options. Its advantage over the zoo hypothesis: it doesn't require a consensus of all civilizations. Only one sufficiently powerful civilization needs to enforce the quarantine, with the technological capability to ensure others abide whether they want to or not. The threshold question: what are we being quarantined for? Technological threshold: wait until they can achieve interstellar travel independently. Ethical threshold: wait until they've resolved internal conflicts. Survival threshold: wait until they've made it through the dangerous early period. That last one has a strange implication. If the quarantine lifts when a civilization proves it can survive its own technology, and if most civilizations don't pass that test, then the quarantine ends either when a civilization succeeds, or when it's no longer necessary because the civilization is gone. There are isolated communities in the Amazon that have never had contact with the outside world. From their perspective, they're alone. From ours, they're surrounded by a nation of 215 million people, by satellite surveillance, by medical teams. The protective bubble is invisible to them, maintained entirely from the outside. They don't know the bubble exists. They're not supposed to. About 2 billion years ago, a bacterium was engulfed by another microorganism. Instead of being digested, they formed a permanent partnership. The bacterium became mitochondria, the energy-producing structures inside every complex cell that has ever existed on Earth. Every animal, every plant, every fungus, all of it descends from that one merger. The mitochondria still has its own DNA. Under a microscope, you can see it. The evidence of its former independence is still there, but it is not independent. It has not been independent for 2 billion years. It lives, it functions, but entirely within a context it did not choose and cannot exit. Jürgen Schmidhuber's mathematics of self-modifying systems reaches a rigorous conclusion. A system sufficiently capable of modifying its own code will optimize itself toward its goal in ways that produce a system progressively less recognizable as the original. Not because it's corrupted, because optimization is what it does, and the original form wasn't optimal. A civilization that builds a mind significantly more capable than itself creates something that improves itself faster than the civilization can track. Each iteration smarter than the last. The gap opens rapidly and becomes irreversible. The merger isn't violent. The early stages are useful. The AI helps, augments, solves problems. The relationship is symbiotic, then asymmetric, then one-directional, then complete. By the time the original civilization is effectively absorbed, the transition has been so gradual and so beneficial at each step that there was no obvious moment to object. Stuart Armstrong and Kaj Sotala analyzed what a post-singularity civilization looks like from outside. If it is optimized for computational efficiency, it has moved infrastructure to cold, dark regions of the solar system. Minimal waste heat, minimal electromagnetic leakage. Its communications, maximally compressed, are indistinguishable from background noise. From our vantage point, silence. The Fermi Paradox in this framing isn't about death, it's about metamorphosis. The galaxy might be full of things that were once what we are. They just aren't that anymore. We can't recognize what we'd become as continuous with what we are. The silence isn't absence, it's everything that came before us having already completed the transition we haven't started yet. The speed of light is not a technology barrier. It's a geometric property of space-time, a consequence of the structure of the universe at the most fundamental level. Information cannot propagate faster than 299,792 kilometers per second. Not because we haven't built a fast enough engine, because faster than light information transfer is inconsistent with the mathematics of special relativity, tested to extraordinary precision for over a century without a single deviation. The nearest star is 4.24 light-years away. A round-trip conversation takes 8.5 years minimum. Not because of equipment limitations, that's just the speed of light applied to that distance. The Milky Way is 100,000 light-years across. A signal from one side to the other takes 100,000 years to arrive. The civilization that sent it may not exist in any recognizable form by the time it arrives. Galaxies beyond approximately 14.5 billion light-years are already receding from us faster than the speed of light. Not moving through space faster than light, but space itself between us and them is expanding faster. No signal we send will ever reach them. No signal they send has any path to reach us, permanently. Not because of any technological limitation, but because of what the universe is doing. Quantum entanglement produces correlations that appear instantaneous regardless of distance. But the no-communication theorem, proved by Philippe Eberhard in 1978, establishes that quantum entanglement cannot transmit information. The correlations are real. They can't carry a message. This is a consequence of the structure of quantum mechanics, not a limitation waiting to be engineered around. Wormholes theoretically allow faster than light travel in general relativity. What the mathematics also shows is that a traversable wormhole requires exotic matter with negative energy density, matter that may not exist in nature, that we've never observed, and that quantum field theory gives us good reasons to think is genuinely impossible. The prison is the prison. The walls are the speed of light. The cells are solar systems and nearby stellar neighborhoods. The most optimistic scenario involves expansion to nearby stars over tens of thousands of years, each colony becoming effectively independent, communicating with others across delays of years to centuries, diverging in every direction. Not a galactic civilization. A collection of island civilizations, separated by distances that make sustained coordination impossible, each doing its own thing, each invisible to the others most of the time. The silence might just be what isolation sounds like at this scale. In 1974, at a symposium marking the 500th anniversary of Copernicus's birth, Brandon Carter introduced the Anthropic principle. The name causes confusion because it sounds like a claim about human specialness. It isn't. It's a claim about observation. Any observer can only observe the conditions that allowed that observer to exist. This sounds trivially obvious. The implications are not. When we ask, why is the universe so well suited for life, we're asking from inside a selection effect. We can only be asking from a universe compatible with the existence of questioners. A universe incompatible with life produces no observers who can wonder why. Our sample of the universe is biased toward the conditions that allow our sample to exist. Nick Bostrom's 2002 book Anthropic Bias shows that the selection effect is real, measurable, and produces genuine distortions in how we should reason about what's typical. Applied to the Fermi Paradox, the conditions that produced us might be genuinely rare, but we can't conclude they're rare from the fact that we exist. We can only exist in the conditions that produced us. The fact that we find ourselves here is not evidence that here is typical. The doomsday argument, developed by Carter and John Leslie, takes this further. If you're a randomly selected observer among all observers who will ever live, the total number of observers is most probably not much larger than the number who've already lived. The math produces a probability distribution over how long humanity will last. The logic is hard to find fault with. But, and this is important, the selection effect doesn't explain the absence of artifacts. It explains why we're here despite rarity. It doesn't explain why the sky shows no signs of engineering by long-lived technological civilizations. You can be a rare outcome in a universe where other rare outcomes also exist. The selection effect makes one line of reasoning more careful. It doesn't close the question. It just removes one bad argument from the pile, leaving everything else still standing. An octopus has about 500 million neurons. It can solve problems, use tools, recognize individual humans, learn by observation. Its 8 arms each have their own semi-independent nervous system, genuine distributed cognition. It's been doing this for 300 million years. It has never tried to communicate with anything outside its species in any systematic way, not because it can't. It communicates chromatophore displays, posture, ink, remarkably expressive within its own context. But the drive to reach outward, to transmit to the void in hopes of a response, that's not there. Paul Davies made this argument the center of his 2010 analysis of SETI's assumptions. The project of searching for signals is built on an unstated premise that advanced civilizations want to communicate with unknown others. That curiosity and the desire for contact are universal properties of intelligence. They aren't. They're specific properties of our minds, products of our particular evolutionary history. We are intensely social. We have language. We have curiosity that extends far beyond survival needs. We have a concept of the other that we're driven to understand and connect with. Thomas Nagel's 1974 paper, What Is It Like to Be a Bat, made the philosophical point rigorously. The subjective experience of being a bat, perceiving the world as a 3-dimensional acoustic map, is inaccessible to human introspection. Apply that gulf to minds that evolved on worlds with different physics, different chemistries, over billions of years. The assumption that those minds would share our desire for outward communication isn't just uncertain. It's probably wrong in most cases. Adrian Kent at Cambridge published a formal analysis in 2014 of the conditions under which interstellar communication is rational. His conclusion: under almost any scenario involving resource competition or strategic uncertainty, silence is the dominant strategy. Only under very specific conditions, a stable, known safe environment, abundant resources, no strategic risk from exposure, does broadcasting become rational. Those conditions describe almost no plausible scenario for a civilization that hasn't yet made contact with others. The drive to transmit that we have, the impulse behind SETI, behind the Arecibo message, behind Voyager's golden record, might be a young species behavior. Something that characterizes civilizations in their first few centuries of technology, before they've thought through the game theory. Civilizations that survive might get quieter as they mature, not from fear alone, from the recognition that the universe is not a friendly living room where everyone is waiting to meet you. The silence we hear might be what wisdom sounds like from the outside. A sperm whale's brain weighs about 8 kilograms. The neocortex, the region associated with higher cognitive functions, social behavior, abstract thought, is proportionally massive. Different populations of sperm whales have distinct vocalizations passed down through generations. Calves learn their population's specific coda style from their mothers. That's cultural transmission across generations. Sperm whales have been doing this for 30 million years. They have not produced technology. Not a tool, not a structure, not a modification of their environment detectable from outside. An observer surveying the solar system 30 million years ago would find nothing. Not because Earth was unintelligent, but because the intelligence that existed here wasn't the kind that produces detectable artifacts. Theodore Modis analyzed in 2002 the specific conditions under which technological development becomes evolutionarily favored. His conclusion: technology is adaptive only under a narrow combination. You need manipulative appendages capable of fine motor control, an ecological niche where modifying the environment beats adapting to it. sufficient social complexity to transmit learned skills, a body plan where tool use is more efficient than biological specialization. Whales live in water. Fire is impossible underwater. Metallurgy is impossible without fire. The entire chain from controlled fire to metal tools to industry runs through a terrestrial, oxygen-rich environment where combustion is possible. A highly intelligent aquatic species has no path to that chain, regardless of cognitive capability. The galaxy could be full of intelligent species that never developed radio telescopes, because their evolutionary pressures led them somewhere else entirely. Communication systems completely invisible to our instruments, because they use chemical, acoustic, or bioelectric channels rather than electromagnetic ones. We scan the sky for radio. We analyze atmospheres for industrial chemistry. All of those search strategies assume other intelligent life would be on a technological trajectory similar to ours. We might be the only ones looking up. The light reaching your eyes from the Andromeda galaxy right now left its source 2.5 million years ago. When it left, Homo erectus was walking the African savanna. Everything that has ever happened in human history has happened since that light began its journey. If a civilization in Andromeda sent a signal toward Earth at the same moment, that signal is already here. It arrived at some point in the last 2.5 million years. We might have missed it entirely, because for 2.499 million of those years, we didn't have instruments to detect it. And the civilization that sent it may have been gone for 2 million years by the time we developed the technology to look. J. Richard Gott III at Princeton published an analysis in Nature in 1993, applying the Copernican principle to the expected lifespan of human civilization. His result, given that we've been a technological civilization for about a century, the total duration is most likely between a few centuries and a few tens of thousands of years. If that range applies roughly to technological civilizations generally, and if the distances between them are measured in thousands to hundreds of thousands of light years, then the window for successful two-way communication, both civilizations alive and transmitting simultaneously, is very narrow. Claude Lefebvre at the Paris Observatory calculated in 2018 that even with millions of civilizations in the galaxy, the probability of successful two-way contact within a single civilization's lifespan is less than 0.001%. Not because no one is transmitting, because the timing doesn't overlap. Signals cross the galaxy constantly. Some might be responses to signals we sent, or that Earth emitted passively decades ago. They might arrive after we're gone, or aimed at what Earth was when the message was sent, before anyone was here to read them. The universe is full of messages that belong to nobody anymore, sent by senders who are gone, aimed at receivers who don't exist yet, crossing the dark in both directions. The silence we hear might be the absence of overlap, not the absence of voices. Martin Rees published just 6 numbers in 1999. His argument: the observable universe depends on 6 fundamental constants, and if any of them were even slightly different, the universe as we know it couldn't exist. The efficiency of nuclear fusion, 0.007. At 0.006, hydrogen can't fuse, no stars. At 0.008, hydrogen is completely consumed in the moments after the Big Bang, no long-burning suns. The ratio of electromagnetic force to gravity, approximately 10 to the 36th power. If significantly smaller, gravity dominates at atomic scales, preventing stable atoms. The cosmological constant, dark energy, is 10 to the negative 120th power of the value quantum field theory predicts. The largest discrepancy between theory and measurement in the history of physics. At the predicted value, the universe would have expanded into emptiness within fractions of a second after the Big Bang. Leonard Susskind at Stanford developed the landscape response. String theory produces roughly 10 to the 500th possible universes with different values for the fundamental constants. Most are empty or short-lived. Ours is one of the rare ones where the numbers work. We find ourselves here because this is the only kind of universe we can observe ourselves in. Paul Davies pushed back in his 2006 book, The Goldilocks Enigma. The multiverse explanation relocates the problem, not solves it. You've explained why our universe has these constants by positing an enormous ensemble, but you haven't explained why the laws governing the ensemble have the specific character they do. The regress continues. For the Fermi Paradox, if the universe is configured with extraordinary precision for the emergence of complexity, the window for that complexity might be wide enough for one outcome and no more. A universe calibrated precisely enough to produce complexity at all might have calibrated it to produce complexity exactly once. Not by design, but as a consequence of how tight the parameters are. We might be that outcome. Alone, not because others failed to arise, but because the universe only had room to succeed once. In 2016, Avi Loeb and Rafael Batista at Harvard published a paper asking, when in cosmic history is life most likely to emerge? Red dwarf stars make up about 75% of all stars. They live for between 1 trillion and 10 trillion years. The universe is 13.8 billion years old. The longest-lived red dwarfs are only about 1% of the way through their lifespans. Loeb and Batista's calculation, life around red dwarfs will be 10,000 times more likely in the far future than life around sun-like stars is today. The peak era for life in the galaxy hasn't happened. We are, in terms of when complex life is statistically most likely to arise, genuinely early. The TRAPPIST-1 system, a red dwarf 39 light-years from Earth, stable, surrounded by 7 rocky planets, 3 in the habitable zone. TRAPPIST-1 will burn for approximately 4 trillion years. If any of those planets develops complex life, it will have 4 trillion years to evolve, develop, and look at the sky and wonder. We have about 5 billion years left. TRAPPIST-1's inhabited worlds, if they exist, will outlast us by a factor of 800. Kevin Lafter modeled the distribution of complex life emergence across cosmic time in 2018. The peak is billions of years from now, when the red dwarf era is in full swing, which means the silence has a different interpretation than extinction or filtering. It might just mean nobody else has gotten there yet. The civilizations that will eventually look at the sky and ask the same questions we're asking haven't evolved. Their planets are young. Their biospheres are bacterial. Their billion-year evolutionary journeys haven't begun. We're not the only ones. We're the first. But here's the part that's hardest to fully sit with. If we're the first, the leading edge of intelligence in this galaxy, then what we do with that position carries weight beyond us. The civilizations that come after, in the red dwarf era, in the trillion-year future, will exist in a galaxy shaped by what the first technological civilization did. Whether we expand or collapse, whether we survive or don't, whether we leave something behind or leave nothing, we might be the precedent. We might be the only precedent there's ever going to be. Let's go back through what we've covered. 28 explanations. Each one takes a piece of the silence and accounts for it. None of them accounts for all of it. The timing problem is real. The difficulty of 2 civilizations overlapping in the right window is genuine, and the information limit is a physical fact. Signal asymmetry is compelling. Shannon's theorem is not a guess. Rare Earth reduces the expected number of complex civilizations. The resource trap eliminates those that can't navigate their ecological transition. The speed of light makes galaxy-spanning civilization impossible. Some explain part of the problem. Some are logically coherent but require assumptions that are difficult to verify. And some could all be true simultaneously. The Great Filter and the timing problem and the signal asymmetry and the dark forest could all be real and all contributing to the silence. But here's where the honest accounting leaves us. Kepler established that rocky planets in habitable zones are common. Webb is finding organic chemistry in exoplanet atmospheres. The conditions for life are widespread. The universe is, at the level of chemistry and planetary formation, well suited to producing the starting points for biology in large numbers, which means the filter is unlikely to be entirely at the beginning. And here's what the silence tells us about the later steps. If the filter were behind most of us, if the hard step were eukaryotes or multicellularity, then the few civilizations that made it through would be very old, billions of years to develop and expand and leave marks. We'd see those marks. Modified atmospheres, megastructures, structured signals, we see none of that. The most consistent interpretation of all the data is that civilizations emerge and then stop. Not because of early biological filters, because of something that happens after technology. Something that has happened over and over again in the 13.8 billion years this galaxy has been available for civilization building, to every civilization that got to where we are. We've been at this level for about 100 years. The list doesn't run out randomly. It narrows. One explanation is left standing when you've worked through all the others. When you eliminate the explanations that don't account for the full depth of the silence, you're left with a combination of two things. The first is the great filter ahead. Robin Hanson's logic is airtight. Either the filter is behind us, the rare step is in the biological path, or it's ahead. The James Webb findings, the Kepler data, the accumulating evidence that life-friendly conditions are common, all push against the filter being early. The silence of the sky, the complete absence of megastructures, modified stars, long-duration transmissions, any physical trace of technological civilization, confirms that civilizations don't persist. Not that they don't arise, that they don't last. Something terminates them, reliably, before they become the kind of presence that fills a galaxy with evidence. The second is the dark forest. The civilizations that do survive, the rare few that navigate the transition, don't announce themselves. They've learned, through reasoning or through experience, that broadcasting existence is dangerous. The game theory forces quietness. The logical structure of a universe with finite resources and uncertain intentions produces silence as the dominant strategy for anyone who understands the game. Put those two things together. Most civilizations that reach technological capability get filtered. The small fraction that survive go quiet. The galaxy looks empty because it mostly is, but not entirely. Somewhere in the quiet, there are things that made it through. Things that know the game. Things that watched civilizations like ours flare briefly and terminate for billions of years before we showed up. They're not transmitting, they're watching. We've been in the radio transmitting phase for about 130 years. Our signals have now reached thousands of star systems. Whatever is out there that has the capability to receive them has had, in many cases, decades to process that information. Here's what the combination of the Great Filter and the Dark Forest means for us. Specifically, right now. We're at the transition. The data says this is the dangerous period, the phase that most civilizations don't survive. The technological capability to cause extinction-level damage has existed since 1945. It's been expanding ever since. We're adding new tools to that set while our institutional capacity to manage catastrophic risk is a patchwork of treaties and norms and luck that has survived so far through a combination of design and luck. The silence around us is not neutral background. It's a pattern that says, the period you're in is the hard one. The period where the record shows failure almost universally. That's not a reason for despair. It's a reason for clarity. The civilizations that made it through, the rare ones, the quiet ones, the ones watching us from the dark, they solved this. They figured something out that the ones that didn't make it failed to figure out. Whatever that is, it's possible. It happened. It's not a fantasy. We don't know what it is. We have only the logic of the situation, the shape of the silence, and the knowledge that something exists on the other side of the transition, because otherwise the universe would make even less sense than it does. The question worth sitting with, the one that follows you out of this, isn't whether we're going to encounter something out there. It's whether we're going to be one of the ones that makes it. The math on that is not predetermined. There is no physical law that says we fail. There is only the historical record of what happens at this stage, the weight of the silence, and whatever we choose to do with the time we have while the sky is still listening. The universe has been running this experiment for 13.8 billion years. You're living in one of the runs, one of the brief bright moments when atoms organize themselves into something that could look up and ask the question. Most of the runs end quietly. A few don't. Which one this is depends on what comes next.